Hello guys, welcome to Self Help Maths Academy. Now we are going to discuss about the next topic, that is linear transformation. So let us understand what is linear transformation. Before that, we need to understand what is transformation. So transformation is basically, it is a function or a mapping, or it's also called as a transformation in itself. It is denoted by T from the space Rn to Rm. Say let T is a transformation from Rn to Rm. This is basically a rule that assigns to each vector x in Rn to a vector T of x in Rm. So basically what we are trying to understand here, when you have when you have a function when you have a function t from Rn to Rm. Okay, so whenever it's like a mapping or a function from Rn to Rm, from one space to another space. So you can understand, if I take x from this Rn, so when I map it to Rn, here that image will be t of x, then the t of x will be in Rm. If x is in Rn, by this transformation my t of x will be in Rm. So then the set Rn is called, this set Rn, this is called as the domain. It is called as the domain of a transformation T. And Rm is called a codomain of a transformation T. Okay, so then this notation, that is T from Rn to Rm, it is indicated the domain of T is Rn. This is the domain of T is Rn, and the codomain of T is Rm. So basically transformation is nothing but it is a function or it is a mapping from one space to other space. Okay, now for instance, say for x in Rn, the vector, when I already explained you, when you have your function from x, if this is say from Rn to Rm you have, so this is your t. So whatever you have here, the element x in Rn, when I after transforming that in Rm, we will get it as t of x. So for x in Rn, the vector, the t of x in Rm is called the image of x. This is called the image. The t of x is called the image of the element x. Now like that, you may, for x it may be t of x, for maybe x1 t of x1, x2 t of x2, like that you have a collection of images. So the set of image, the set of all the images which we obtain here, that is called the range. That is called the range of T. That is called the range of T. So what happens here? Why we are calling it as a transformation? We would have called it as just a basic function, right? As it is like we have function or a mapping, like that we would have called this as a function. But what happening in this case is, suppose like this particular figure, I'll explain you once we see this example. Suppose you have this matrix, when you multiply with the vector x which is in R4, if you see. Okay, so here what is happening, there is a transformation happening here. When I multiply this particular matrix with R4, the vector is in R4, I get the result vector in R2. So what is happening is, we are transforming the vector from R4 to R2. That means the vector, this x vector, it was in R4. This vector got transformed. When I multiplied by the vector, the multiplication of the matrix is A, both the side I am multiplying with the matrix A only. It was in R4 and it got transformed to R2 space. Okay. Similarly, in this example, if you see, it is a matrix A and there is a vector U here which is in R4, and then if I multiply this with the matrix A, I'll get the matrix which is 0 0 matrix, which is in R2. So that means what I am transforming the given vector from R4 to R2. This transformation is happening here. It was in R4, it got transformed to R2. That's why it is called transformation. Okay, that's why we are using the term as transformation. Okay, now we have to understand what is the matrix transformation. So here, for each x in Rn, T of x is computed as say A into x. We write now T of x as some A into x, where A is our m cross n matrix. So this T of x, the image which we were talking about, where x is transformed to T of x, I am writing my T of x, this image, as A into x, where A is a m cross n matrix. Okay. If for a simplicity, sometimes we denote such matrix transformation, because now if you see, the transformation is the resultant image you're getting is in terms of matrix A into the vector. So A is a matrix here. Okay. So that's why it is called as now matrix transformation. So it involved the matrix now, right? So it is called matrix transformation. Observe that the domain T. Okay. So the domain of the T is Rn, like we have seen in previous definition. T is from Rn to Rm. So this Rn I'm talking about, this Rn is a domain of T when A has n columns. So I said this A is a m cross n matrix, right? M cross n matrix where it has m rows and n columns. So A has n columns and the codomain of T is Rm. So this is a domain and this is a codomain. Okay. When each column of A has m entries. So when each column of m has how many entries? M entries, because it has a m rows. Okay. So that's the simplification. Then we call that as matrix transformation. Okay. So this is the basic understanding of transformation. We have still not gone to the linear transformation. So now we will understand what is linear transformation. Okay. So the linear transformation, the definition says a transformation or a mapping or a function, you can say, okay, mapping T is linear. It is linear if it has to hold two conditions. The first condition is if T of u plus v is equal to T of u plus T of v. So usually a transformation, a mapping, it is the T which we define. Maybe you can consider T from say v to w. Okay, this is a function which is said to be linear if it follows these two conditions. For all u and v in the domain, that is in the domain means what? Domain of T, or u and v belongs to v, that is a domain. Okay. Second condition is that is T of c into u is equal to c into T of u. For all say u belongs to v and c is any scalar. Okay, you can take it as any scalar. If then we call it as linear transformation. So let's try to understand what is this. Okay, let us try to understand. Now for the linear transformation, let us try to understand this definition with the help of example. What is this? Suppose, as I told you, when I say that it's a transformation, to say that is a linear, it is a domain and it is a codomain. So you just take any element here, it has to transform to some element in W. Okay. But in this case, let me take an example of say the function which is like some the differentiation function. For example, what I do, my T is a differentiation function where I am taking this is my function. Okay, so t of 2x square plus 3x plus 1. So what is the derivative of this element, this particular function? If you see, 2x square derivative is 4x and 3x derivative is say 3. Okay, and now let me take another function which is like t of x square minus 1. So the derivative of 2x x square is 2x and derivative of 1 is 0. So it is just simply 2x. Now let us understand this first property. It says t of u plus v should be equal to t of u plus t of v. So in this case, is it possible? So here, if I take t, this is my, let me take this as u and this as v, and if I add this I'll get. That is nothing but t of 2x square plus x square is 3x square, and 3x minus, 3x, that is 3x, and plus 1 minus 1 cancel. So this is my function. Now you know that my transformation here is the finding a derivative. So this one will be, the derivative of this will be 6x plus 3. Let me take this as 1. Okay, so let me take now individually what is our t of u plus t of v. So already know this is our t of u, this is 4x plus 3, and t of v, that is 2x. So adding these two also gives me 6x plus 3. If you match 1 and 2, that is one another same. So basically now this here what happens in the differentiation, that is the the meaning. So here what you by doing this particular differentiation transformation, what I got the first property, it holds true. For example, let me take another example. If I take a derivative, say d by dx of say 6x square, this is same as 6 into d by dx of x square. Okay, this is what it is true. Now what is the derivative of 6x square? It is just 12x, and here it is 6, and x square derivative is 2x, which is again 12x. So if you see, this is nothing but what? This is nothing but t of, because my transformation is here differentiation, so t of c into u is as same as c into t of u. Okay, so the both the properties are satisfied by this particular example. So then we can call this as a linear transformation. So that is the simple understanding of linear transformation. Now let us understand this particular transformation with help of some of the example. Okay, so let us take another example. So here the example says, let t is a function or a transformation from R2 to R2, which is defined by say t of x y. This is equal to 2x plus 3y minus x plus 4y. Okay, this is how it is defined. Now let us check whether this is a transformation, it's a linear transformation or not. This is how it is given. So how do we solve it? The solution goes like this. Now let our u is, let me take one u, say this is my x1, y1. Let me take my v as say x2, y2. Okay, so these are belongs to, where c also, let me take a scalar, c belongs to r. Okay, so what is the first condition? T of u plus v should be equal to t of u plus t of v. Let us check that. So this is t of, what is my u, v plus v will be, u is x1, y1, and if I add this is like my x2, and this is our y2. Okay, so now this is equal to, so this is our now, this is how it is defined. T of x comma y is defined as 2 times of x plus 3 times of y. So now this is our x and this is our y. Therefore, this will be written as 2 times of x, that is x1 plus x2 plus 3 times of y, that is y1 plus y2. Okay, and similarly for the second, we have defined it as minus x plus 4y, the second row. So minus x, minus of, this is our x, x1 plus x2 plus 4y, that is y1 plus y2. Okay, now simplify this. Let us see. This will be equal to what we get. So this is, now you can write this as 2x1 plus 2x2 plus 3y1 plus 3y2. This is minus x1 minus x2 plus 4y1 plus 4y2. Okay. And also we can write this as further. This is 2x1 plus 3y1. Let me write this way. And 2x2 plus 3y2. This is minus x1 plus 4y1 plus minus x2 plus 4y2. This is equal to. Now let me write this as 2x1 plus 3y1 minus x1 plus 4y1 plus 2x2 plus 3y2 minus x2 plus 4y2. Now if you see this, it is as the pattern as given by t of xy. So here this is nothing but my t of u. This is our t of u and this is our t of v. So we started with the t of u plus v. So we got the first property. Okay, the first property. Now let us check. This is called additivity, right? The first property is called as additivity. And second one is called as homogeneity. Okay, it's called as homogeneity. So let us check that also. T of c into v is equal to T of, this is c into x1, c into, what is our, this one is c into x2. Okay, let me take this as v, x2 and y2. Okay, so this is equal to, now 2 times of x1 plus 3 times of y2, so it is 2 into cx2 plus 3 into cy2, and here it is minus cx2 plus 4 into cy2. Okay, as per the definition we are writing this one. So this one is equal to, if I take c out on both the side, it is 2x2 plus 3y2 minus x2 plus 4y2. Okay, so this is nothing but what, c into t of v. So you started with the t into c of v. So this is our second property. So both the properties are satisfied for the transformation. Hence t is a linear transformation. It is a linear transformation. Okay. So you may wonder now, is every time it is possible that we will get all the transformation as a linear transformation? So the answer is no. In some cases we may not get the linear transformation. So let's see some examples. Suppose let t is a transformation from R2 to R2, which is defined by, let me write as t of xy, that is equal to, t of xy is equal to x square y. Let us check this is a linear transformation or not. So to start, let me take my u as say x1 y1. Okay, and let me take v as x2 y2. Let us take some c, which is a real. So now to check our additivity, that is the first property. So now what we do, t of u plus v is equal to, so t of x1 plus x2 y1 plus y2, this is equal to, so it is defined as x square. You see xy is defined as x square y. So here x square y means this is x1 plus x2 square upon y, that is y as y1 plus y2. Okay, now this is our LHS. Let me take now t of u plus t of v. This is equal to, t of u is what? It is x1 square y1 x2 square y2. So now this is equal to x1 square plus x2 square y1 plus y2. Okay, if you observe here, since if you see here we have got x1 So here you can see this is x1 plus x2 square, but here it is just x1 square plus x2 square. So therefore x1 plus x2 square cannot be equal to x1 square plus x2 square. So therefore our additivity fails. General additivity, in general our additivity, the first property fails. Additivity fails. So if one property fails, then it is not a linear transformation. Okay, therefore T is not a linear transformation. It is not a linear transformation. Okay, let us see another example. Now let us take T is from R3 to R be defined by T of say x, y, z equal to x plus y plus z. So is it a linear transformation? So to check that, now we will start with, let us take, let u is say x1, y1, z1 and v is say x2, y2, z2 and say c is any real number. So additivity, that is T of u plus v is equal to T of x1 plus x2, y1 plus y2, z1 plus z2. This is equal to, as per the definition, it should be x1 plus y1, then yeah, it has to be x plus y plus z. So x1, let me write this as x1 plus x2 plus y1 plus y2 plus z1 plus z2. Or if you want, you can just write this as x1 plus x2, y1 plus y2 and z1 plus z2. Or if you want, you can just write it as x1 plus y1 plus z1, x1 plus y1 plus z1 and x2 plus y2 plus z2. So this is nothing but your T of u and this is nothing but T of v. So therefore the first additivity property holds true. Similarly, for homogeneity, let us take T of c into v. This is equal to T of c into x1, c into y1, c into z1. Oh, here we have taken, so let me take this as 2. Okay, so this is basically by writing cx2 plus cy2 plus cz2 by the definition, right? So if I take c out, it is x2 plus y2 plus z2. So what is this? This is nothing but c into T of v. So started with T into C of v, we got C into T of v. So therefore both the conditions satisfied. Hence we can say that T is a linear transformation. T is a linear transformation. Okay. Now another example. Let us take another example where we will take, let T is a transformation from R2 to R2 be defined by say T of xy is equal to say x plus 1 y. Okay, let us see whether it obeys the linear transformation or not. So here what I take is, let me take a zero transformation, because if it is a linear transformation, let me give you a note here. The note, before I continue with the example, the note is, if T is a linear transformation, okay, T is a linear transformation, then T of 0 should be equal to 0. Okay, T of 0 should be equal to 0, and then T of say C times of U and D times of V you have, then it is C into T times of U plus D into T times of V. This is true for all the U and V belongs to U. Okay, this is true for all UV belongs to U and your C belongs to R. Okay, so this is very important. This is the important note we have to know. So now sometimes no need to check all the properties. What we do, we'll check for, in this case what we do is we check whether the zero the whether the zero vector belongs to this particular transformation or not. So let me take a zero vector. Let 0 equal to say 0 0. So then what should be our t of 0 0 should be? T of 0 0 should be, as per this definition, it should be now in place of x and y I'm taking 0 0. So it should be 0 plus 1 0 here. So it is 0 plus 1 0. So which is 1 0. But if I take a 0 image, it should be 0, right? So therefore this is not equal to 0 0. So therefore t, actually the transformation t fails to preserve the 0 vector. Okay, here what happens? So t fails to preserve the 0 vector, which implies that at least one of the two properties fails. Okay, so it means what? One of the two properties fails. If you want, you can just check with the by taking the elements. For example, I want to take, say, let me take u as say x1 y1 and v as say x2 y2. So this is enough to say, but if you want to just check, I'm doing this one. Say t of u plus v, which is equal to say x1 plus x2 and y1 plus y2. So this is our x1 plus x2 and y1 plus y2. How it is defined? It is defined as x1 plus x2 plus 1, and this is simply y, right? Because that's how it is defined. This is simply y1 plus y2. Okay, now let us take our t of u plus t of v. So t of u is x1 plus 1 y1 and t of v is x2 plus 1 y2. So this is nothing but what? x1 plus x2 plus 2 and y1 plus y2. If you observe carefully, if you see this, in this here we have got x1 plus x2 plus 1 and here we have got x1 plus x2 plus 2. So x1 plus x2 plus 1 is not equal to x1 plus x2 plus 2. Hence it fails to be a linear transformation. Therefore T is not a linear transformation. Okay, linear transformation. This is how you have to conclude that whether it is a linear transformation or not. So now let me give you some examples. Just try them and answer me in the comment box. If I have, let T is a transformation from R2 to R be defined, it is defined by say T of xy is equal to some 7. Okay, whether it is a linear transformation, just check. And another one, if it is t is same from r2 to r2, this is from r2 to r. Let me write, this one is from r2 to r, and let me give you another one. Second one, let T is a transformation from R2 to R2 defined by T of xy equal to x negative y. So check whether they are linear transformation or not. If they are linear transformation, give the valid reason. If they are not, also give the valid reason, and comment your answers in the comment box. If you like the video, please do subscribe and share with your friends so that it will be helpful to others. Okay, I think this is all in this video. Maybe in the next video we'll come up with the matrix representation of a linear transformation. Till then, take care guys. Bye bye.